Module 9, Lecture B, Open and Globals. By the end of this lecture, you will be able to use Open with Context Managers to read from and write to files safely, specifying modes and encodings. Inspect and, when necessary, modify global and local namespaces using globals and locals in controlled scenarios. And use import for dynamic imports while understanding its risks and preferring higher-level alternatives when possible. Safe file opening. Text and binary modes. When you open a file, choosing text mode means the file is treated as human-readable characters rather than raw bytes. In this mode, the system automatically converts between bytes and characters so you can work directly with strings. It also handles differences in line endings across operating systems, giving you consistent behavior. Text mode is therefore best for natural language or structured text formats, where you want the system to manage encoding details for you. Binary mode treats a file as a sequence of raw bytes, instead of trying to interpret it as characters or lines of text. This is essential for non-text data, such as images or audio, where each byte has a specific meaning defined by the file format. If such files are opened in text mode, the system might try to decode or alter the bytes, which can corrupt the data or cause bugs. Using binary mode preserves the file's contents exactly as stored, maintaining data integrity and compatibility with other tools. Choosing between text and binary file modes is important for keeping data correct and uncorrupted. Text mode is best for human-readable content like logs or configuration files because it works naturally with strings and lets the system handle encodings and line endings. Binary mode is needed for structured binary data such as medical images or firmware, where you must control the exact bytes to ensure compatibility with other systems. Well-designed programs clearly document whether each file is text or binary, which improves maintainability, reduces errors, and helps keep the data flow clear. Python code, text, and binary modes. This lesson shows how to read and write data in both text and binary modes. You will see simple examples of working with string content in text mode and raw byte content in binary mode. By comparing the two, you will observe how the same underlying bytes are represented and displayed differently depending on whether you use text or binary mode. The code defines a variable that stores the name of a text file called example_text.txt. This file name will be used later in the script for reading from and writing to the file. By keeping the file name in a single variable, the code can reuse it easily and change it in one place if needed. The code stores a specific file name in a variable to represent a binary file. This sets up a path where raw byte data will be saved and later read back in the script. Using a separate name for this binary file helps the program clearly distinguish it from other files and file types it may handle. In this example, a text content variable stores a string that says "Hello World," then uses a new line character before a second sentence that says "Second line here." This simple setup illustrates how text files represent character data, including line breaks, when working in text mode. It shows that new line characters in the string control how the text appears across multiple lines when the file is read or written. This example creates a sequence of raw bytes that correspond to the ASCII values for the characters in the word hello, followed by a comma, a space, and a special byte with the value 255. The sequence is stored as binary content to show how raw byte data can be represented directly. The main goal is to illustrate how such binary data is used in file operations that work in binary mode, as opposed to text mode operations that work with ordinary character strings. We open a file named example text in write mode and specify UTF-8 as the encoding, so any text we write is stored using that character format. Using a with statement sets up a managed block that automatically closes the file when we are done. This approach both ensures correct text encoding and helps prevent resource leaks by handling file closure for us. The code saves text into a file by calling the write operation on a text file object. This operation takes the string content and stores it as characters in the file. As a result, the information is preserved in a readable text format that can be opened and viewed later. We open a file in binary write mode when we want to store raw byte data instead of text. Using this mode tells the system that the file is for writing and that all data will be treated as bytes. This is important for saving non-text information, such as images or other binary formats, where character encoding does not apply. This code writes binary data directly to a file by calling the write method on a file that has been opened in binary mode. The method takes a sequence of bytes and stores them exactly as they are, without converting them to text. This approach is important when saving non-text data, such as images or executable programs, where the precise byte structure must be preserved. This line prints a message to the console to explain what happens when you read a file in text mode. It tells you that the file's contents will be shown as characters arranged in lines. This helps set your expectations for how the data will appear. It also highlights that this behavior is specific to text mode, which is different from how data is shown in binary mode. We open the file called example text in read mode using UTF-8 encoding, so its contents are interpreted correctly as text. This lets us read the entire file as a string based on the UTF-8 character set. By using a context manager, the file is automatically and safely closed after reading, even if an error happens during the process. The program reads the entire contents of a text file into a single variable using a method that retrieves all characters at once, including newline characters. This means the whole file is stored as one long string. Having the text in this form makes it easy for the program to process, modify, or display the file's content later on. This code prints the contents of a text file in a way that reveals how it is stored in text mode. It uses a function that shows the full string representation of the data, including special characters such as newline markers. As a result, you can clearly see the exact structure and formatting of the text inside the file. This line explains that the file is being read in binary mode, which means you see the raw byte values instead of characters or text. Reading a file this way lets you examine the exact underlying data stored in it. This approach is especially useful for non-text files or whenever you need to work directly with the precise byte content. We open the file named example-binary.bin in binary read mode, so we can access its raw bytes instead of treating it as text. Using a with statement automatically handles opening and closing the file. This is good practice because it ensures the file is properly closed when we are done, which helps prevent resource leaks and other issues. The code reads the contents of a binary file into a variable, capturing the raw byte data exactly as it is stored. This means the data is not interpreted or converted into text, but kept in its original binary form. Working this way is important when dealing with non-text files or when you need precise control over individual bytes. It allows you to manipulate the data at the byte level without any automatic changes. This line displays the binary data that was read from the file, showing the actual byte values directly. These bytes can include characters that are not normally printable. Unlike text mode, which interprets bytes as readable characters, binary mode reveals the raw underlying data. This makes it easier to see how data representation differs between binary and text modes. We are printing the length of the binary data to find out how many bytes it contains. This length is calculated from the data that was read from the binary file. Knowing the number of bytes tells us the size of the raw data we are working with. This gives a clear sense of how much binary information is being processed. In this example, we open the text file in binary mode, so we can work with its raw bytes instead of treating it as regular text. Viewing the file this way reveals the exact byte values that store the characters. This helps us understand how text is represented at a lower level in the computer. It also lets us compare what we see in binary mode with what we saw in normal text mode, making the differences between the two clearer. The code reads the file while it is opened in binary mode, which means it retrieves the raw bytes instead of treating the contents as text. This allows you to see the exact byte representation stored in the file. That representation can differ from how the same data would appear if the file were opened and interpreted in text mode. In this example, we display the bytes of a text file when it is opened in binary mode. This reveals how the same file content looks as raw byte data, in contrast to how it appears in normal text mode. Seeing the underlying bytes helps clarify the difference between text and binary file handling. It also illustrates how text files are actually stored at the byte level, which is important for understanding how different file modes work. This script shows how text and binary file modes behave differently in Python. It writes a normal string to a text file and a sequence of bytes, including one with the value 255, to a binary file. When the text file is read in text mode, you see readable characters and lines, but when the binary file is read in binary mode, you see the raw byte values instead. The script also reads the text file in binary mode to reveal the underlying bytes that represent the text. Overall, it highlights that text mode interprets bytes as characters, while binary mode treats them as raw data, which is important when working with non-text files or specific byte sequences. With statement basics. When working with files, it is important to make sure they are always closed properly, even if an error happens. Using the with statement in Python automates this by opening the file at the start of the block and closing it automatically when the block finishes. This cleanup happens even if something goes wrong inside the block. This approach helps prevent resource leaks in long-running programs, which can otherwise slow them down or cause them to crash. You can think of the with statement as marking a clear region of code where a file is open and in use. Inside this region, you can safely read from or write to the file. And once you leave it, the file is automatically closed and no longer available. This makes it easier to see exactly where the file matters in your program, such as when processing a large server log. It also helps teams work more reliably because everyone can trust that files are handled and closed safely. The with statement is important for writing reliable programs that handle errors safely. When working with files, such as recording sensor data, an error can occur partway through and leave the file open, causing incomplete data and resource problems. Using a with block automatically closes the file, even if something goes wrong, which reduces the risk of corruption and makes recovery easier. This careful handling of resources is especially critical in areas like finance and healthcare, where dependable file operations are essential. Python code. With statement basics. Use the with statement to open files safely because it handles closing the file for you. This is better than manually closing the file, where you must remember to call the close operation yourself. With a with block, the file is automatically closed as soon as the block finishes. This automatic closing happens even if an error or exception occurs inside the block, which makes your code more reliable and easier to maintain. We open a text file in write mode with UTF-8 encoding, which gives us a file object we can use to store data. We then write a line of text explaining that when we handle files manually, we are responsible for closing them ourselves. To finish, we explicitly call the close method on the file so that all system resources are properly released and the data is safely saved. Using a with block to open a file ensures that the file is automatically closed when the block finishes. In this example, a file named example_with is opened in write mode with UTF-8 encoding, and a line of text is written to it. The with statement takes care of closing the file for you, even if an error happens while writing. This makes file handling safer and more convenient than manually opening and closing files. After the with block finishes, you can check whether the file has been closed by looking at its closed attribute, which returns true if the file is no longer open. This confirms that the with statement automatically closes the file when the block ends, so you do not need to close it manually. This example uses a try block with a with statement to safely work with a file while handling errors. The file is opened in write mode, a line is written to it, and then a value error is raised on purpose to simulate a problem. The exception is caught in the except block, where a message encoding the error description is printed. The key idea is that the with statement automatically closes the file even when an exception interrupts normal execution. After an exception occurs inside a with block, we can verify that the file was still closed correctly by checking its closed attribute. This check confirms that the context manager handled cleanup properly. Even though an error happened during execution, the file resource was safely released. This script explains how the with statement in Python simplifies file handling by managing resources automatically. It first contrasts manually opening and closing a file, which requires an explicit close call, with using a with block, where the file is closed for you when the block ends. The script confirms this by checking that the file is marked as closed after leaving the with block. It also shows that even if an exception occurs inside the with block, the file is still closed correctly, demonstrating that this approach is a safe and reliable way to manage files. Encoding and newline basics. When working with text files, it is important to choose the correct character encoding, because encoding defines how characters are stored as bytes. If the program that writes a file and the program that reads it use different encodings, the text can appear corrupted or cause errors. Although many modern systems use Unicode encodings, such as UTF-8, defaults still vary. To keep your code robust and portable, especially for files shared across systems or kept long-term, you should always specify the encoding explicitly. When working with data from different regions or organizations, it is important to clearly specify the character encoding being used. If one system uses an older regional encoding and another assumes UTF-8, characters such as accented letters can be misread and the data may become corrupted. By consistently using a well-supported encoding like UTF-8 and documenting this choice, you reduce the risk of data loss and make collaboration easier. This clarity also helps when integrating with external systems, including web services that often require a specific encoding. When working with text files, it is important to understand how different operating systems represent newlines, because they use different byte sequences for line endings. Many programming tools offer a text mode that normalizes these newlines so your code behaves consistently across platforms. You can either enable this normalization, which is useful for tasks like parsing logs or datasets, or disable it when the exact newline bytes must be preserved, such as with some scientific instruments. By managing both text encoding and newline handling carefully, you keep your text accurate and portable throughout your software's lifecycle. Python code, encoding, and newline basics. This material explains how to explicitly choose a text encoding when writing and reading simple text files and why that matters for correct handling of characters. It also shows how new line translation can change line endings between operating systems, such as Windows, macOS, and Linux. Finally, it guides beginners in selecting appropriate encoding and newline options so their text files remain portable and behave consistently across different platforms. The code first imports the path class from the pathlib module to handle file system paths in a way that works across different operating systems. It also imports the dedent function from the textwrap module, which removes common leading spaces from each line in a multi-line string. Together, these tools prepare the code to manage file locations and clean up text formatting in the rest of the program. We begin by creating a path object that represents a folder named Encoding Newline Demo Folder, using the path class from the pathlib module to handle the file system path. We then call the makeDirectory method on this path and allow it to succeed even if the folder already exists. This ensures the folder is present and ready to use. Setting up this directory is important because it will hold the files used later in the script. This code prepares two file paths inside a folder named for an encoding and newline demonstration. One path points to a text file that will use UTF-8 encoding, and the other points to a text file that will use Latin 1 encoding. The paths are created using the path object from the pathlib library, which offers a convenient, cross-platform way to work with file system locations. This setup is used to get ready for writing to and reading from these files with specific encodings and new-line behaviors. The text content is a short sentence that reads, "Cafe on Main Street, mile 3.5, and it includes an accented letter E. This special character is used to show how different text encodings handle non-standard characters. The same text is then written to files using different encoding and new line settings. By comparing the results, you can see how these choices affect how text is stored and later read on different systems. We open the text file in write mode and explicitly set the encoding to UTF-8, so all written text uses that character set. We also specify Unix-style line endings, which use a single new line character. Within this setup, we write the text content to the file and add a new line at the end of each line. This approach keeps the file's line endings consistent and makes the text more portable across systems that expect Unix-style new lines. We open the target file for writing using the Latin 1 single byte character encoding and explicitly set the line ending to a carriage return followed by a line feed, which is the standard on Windows systems. Within this context, we write the text content to the file and add a Windows-style new line after each line. This approach ensures that all line endings in the file follow Windows conventions, which helps maintain compatibility when the file is shared across different operating systems. The first print statement reports that a file was saved using UTF-8 encoding with Unix-style new lines, which helps keep it compatible with systems that expect that format. The second print statement reports that another file was saved using Latin 1 encoding with Windows-style new lines. Together, they show that you can control both the text encoding and the new line style when writing files, and that different operating systems often use different new line conventions. We open the file using the given path with UTF-8 encoding so that text is read correctly. By letting Python handle new lines automatically, different new line styles are converted into a single standard form. We then read the contents into a list of lines, which makes it easier to process each line separately while keeping the new line format consistent. We open the file using the Latin 1 encoding, so its characters are interpreted correctly. By letting Python handle new lines automatically, all different line ending styles are converted into a single, consistent new line format. This normalization makes the text easier to process. We then read the file into a list where each element is one line, which allows us to work with the content line by line. The code explains that when a file is read with the new line setting left as none, all types of line endings are converted into a single, standard new line character. This creates consistent line endings across different operating systems. It then prints how many lines the UTF-8 encoded file contains after this normalization and shows a sample of the first line. Together, these outputs demonstrate how the file content is read, normalized, and reported. The code prints how many lines were read from the Latin 1 encoded file and shows a sample line to confirm the file was processed correctly. This output helps you check that all new line characters were converted to a single standard new line. The first part of the message explains that you are seeing the line count and a sample of the normalized lines. The second part uses a length operation to count the lines and a representation of the first line to quickly inspect the file's content. We open the file at the given path for reading using the Latin 1 encoding, so the byte data is correctly interpreted as text. The new line setting is left empty, so no automatic new line conversion happens, which preserves the file's original line endings exactly as stored. We then read the entire contents into a variable, giving us direct access to the raw text data, including its specific new line characters. This setup is useful when you need to analyze or process the file in its original, unmodified form. The code first prints a message to indicate that it is showing the raw content of a file encoded in Latin 1, including its original Windows-style new line characters. It then uses a representation function to display the exact byte-level form of the text. This output reveals how the new line characters and other content are actually stored in the file. By examining this raw representation, you can better understand how different new line characters appear in files with various encodings. This script shows how to manage text file encoding and new line handling across different operating systems. It creates one file using UTF-8 encoding with Unix-style new lines, and another using Latin 1 encoding with Windows-style new lines. When reading the files with the new line option set to normalize line endings, all types of new lines are converted to a single standard character. It then reads the Latin 1 file again with raw new lines to reveal the original Windows-style new line bytes. Overall, it highlights why choosing appropriate encoding and new line settings is important for creating portable text files. Globals and locals. Exploring module globals. Module globals are the shared workspace where a module keeps its top-level names, such as functions, classes, and constants. This global namespace is like a mapping from names to the underlying objects, managed by the interpreter while the program runs. Exploring these globals helps you see exactly what is available in a module, which is especially important in larger applications where names may be added indirectly through imports or configuration files. Exploring the global namespace is important when your code needs to adapt to what is defined at runtime. For example, a plugin system can load a module and inspect its global names to discover available functions or classes, and a testing framework can scan global names to find tests that follow a naming pattern. By mapping global names to their objects, you can list features, generate documentation, or build user interfaces that automatically reflect a module's capabilities. This kind of introspection turns the global namespace into useful metadata about how a program is structured and how it behaves. When you inspect a module's global names, you should understand what you are looking at and why. The global namespace includes not only the names you define, but also those added by the runtime, such as built-in attributes and imported modules. It is important to distinguish the stable, intended parts of a module's interface from internal or incidental names. Many teams use naming conventions to mark which globals are public and which are private, and recognizing these helps you use introspection without depending on unstable or unintended details. Python code. Exploring module globals. This section shows how to explore a module's global namespace using the Globals Dictionary. It explains that top-level names in a module, such as functions, classes, and variables, all appear as entries in this global mapping. You learn how to inspect this mapping, filter it to select particular global names, and then print those names along with the types of the objects they refer to. The goal is to understand what is defined at the top level of a module and how those definitions are represented in the global namespace. We define a constant that stores the value 3.14 as an approximate value of the mathematical constant pi, which is commonly used in circle calculations. Placing this constant at the top level of the code makes it part of the module's global namespace. This means it can be accessed and reused anywhere in the module by any function or operation that needs this approximation of pi. The code stores the word Boston in a variable that represents a favorite city in the United States. This variable is defined at the top level of the program, so it becomes part of the global namespace. Because of this, any function or part of the code in the same module can access or change the stored city name whenever it is needed. We create a variable that stores the work commute distance as the integer value 12. This value represents how many miles are traveled each day. By defining it at the global level, it can be accessed and changed from anywhere in the module. This is useful when the commute distance is a common factor used in multiple calculations or parts of the program. This function is designed to return a filtered list of global names and their types for demonstration purposes. It first gets the current global namespace, then creates an empty list to store name and type pairs. As it loops through each global name and value, it skips special names that start with double underscores and also skips certain specific names such as the function itself and the print function. For all remaining names, it records the name and the string form of the value's type. In the end, it returns this filtered list of global names and their associated types. The described globals briefly function collects a list of global variables in a module along with their types. It ignores names that are not relevant, such as those starting with double underscores or certain known function names. The remaining items are stored as pairs of variable name and type in a collection called selected globals. This provides a concise overview of the important global variables and their types in the module's namespace. The code first prints a heading that introduces an overview of the module's global variables. This heading prepares the listener for the information that follows. It signals that the upcoming output will list selected global variables in the module. It also indicates that both the names and types of these variables will be described. The code goes through each selected global variable, taking its name and its type. For every one, it prints the variable's name, followed by an arrow, and then the type of object it refers to. This creates a quick summary of all chosen global variables and the kinds of objects they represent in the module. This script examines the global namespace of the module by using the Globals Dictionary. It defines a few simple global values, such as an approximate value for pi, a favorite city, and a commute distance. A helper function filters out internal names and its own name, then collects the remaining global names along with their data types. When the script runs, It prints this filtered list, giving a brief overview of the key global variables and constants defined in the module. Locals inside functions. When a function runs in Python, it creates its own temporary workspace that holds its parameters and any variables defined inside it, including those from comprehensions or inner functions. The locals function lets you inspect this workspace by returning a dictionary of all these names and their current values. You can think of it as peeking into the function's private notes, where it keeps track of intermediate results and other needed data. For example, in a function that processes survey responses, this might include the current response, a count of valid entries, and a temporary structure used to compute statistics. Understanding how local variables work inside a function is important for debugging and managing complex control flow. By inspecting the dictionary of local variables, you can see which names exist and what values they currently hold, which helps you confirm that data is moving through your code as expected. This is useful in tasks like data cleaning, where you might verify that a cleaned record has the right structure or that a discard flag is set correctly. In more advanced scenarios, such as building a rule engine or a domain-specific language, exposing the current local scope in this controlled way lets you evaluate user-defined expressions without giving access to the entire program state. In Python functions, the locals function returns a dictionary-like view of the current local variables, but it is not meant to be an editable map. Changes you make to this dictionary do not reliably change the actual local variables and can lead to unpredictable behavior. Because of this, you should treat the result of locals as read-only and use it mainly for diagnostics or logging. If you need to manage or modify local data, redesign your function to use explicit data structures that you control, which keeps your code clearer and more reliable. Python code locals inside functions. In this section, we will look at how local variables work inside simple functions. We will see that both parameters and temporary variables appear together in the local variables dictionary for that function. This helps us understand what data is available while the function runs. However, we will also emphasize that changing the local variables dictionary from inside a function is not reliable and should not be used to modify the function's actual local variables. This function takes a text response and a count of valid responses, then first cleans the text by trimming spaces and converting it to lowercase for consistent processing. It checks whether the cleaned response is non-empty and turns that result into a true or false value to decide if the response should be kept. Finally, it prints out all current local variables, including the inputs and any temporary values, to show the state of the function at that moment and help you see what data is available during its execution. Inside the function, we create two local variables representing a feet value of 10 and an inches value of 6 to set up a simple example. We then announce that we are about to try changing these local values. After that, we print their current values to show the starting point before any modification attempts. This prepares us to observe how local variables behave when we try to alter them. The code first takes a snapshot of all current local variables by storing them in a dictionary using the locals function. It then tries to change the values associated with two of these variables inside that dictionary. However, these changes do not affect the actual local variables in the function. When the values are printed, they are the original ones, showing that modifying the dictionary returned by the locals function does not change the real local variables. We begin by printing a message to signal that we are about to call the function named showSurveyStep with an example response. Then, we call this function, passing in a yes response with extra spaces and the number 3. Inside the function, this input is processed, and we can observe how the parameters and temporary values appear as local variables. This demonstration helps illustrate how local variables are stored and viewed within the function's own scope. We call a function that demonstrates the risk of trying to change local variables by editing the dictionary returned by the locals function. Inside this function, two local variables are created with initial numeric values, and these starting values are printed. We then obtain the current local variables as a dictionary and attempt to change the entries for those two variables. However, these changes do not affect the actual local variables, because modifying the dictionary from the locals function does not update the real local state. Printing the variables again shows they are unchanged, proving that altering the locals dictionary does not modify local variables inside the function. This script shows how Python handles local variables inside functions using the locals dictionary. When the SurveyStep function runs, it cleans the input, checks that it is not empty, and then prints the current local variables, including its parameters and temporary values. Another function then tries to change these local variables by editing the locals dictionary. However, the original local variables do not actually change, demonstrating that directly modifying the locals dictionary is unreliable. Overall, the example illustrates how local scope works and the limitations of using the locals function to alter local variables in Python. Risks of modifying namespaces. Directly changing global or local namespaces is powerful but risky because these namespaces control how names are mapped to objects. When you add, remove, or alter names yourself, you can introduce subtle bugs where names unexpectedly change or disappear. This might be tolerable in small scripts, but in larger systems with many modules, such changes can break parts of the application that seem unrelated. For this reason, manual namespace manipulation should be done with great care. Modifying namespaces at runtime can make code harder to read and understand. People expect names inside functions or modules to come from clear sources like parameters or local assignments. When names are injected dynamically, it becomes difficult to follow the logic and to debug, because tools may not reveal these hidden changes. In collaborative projects, this can create confusion and reduce trust, since contributors may not realize that globals or locals are being manipulated behind the scenes. Treating namespaces as containers that external inputs can freely change is risky for both security and maintainability. Letting outside data modify global or local variables can override critical values or bypass safety checks, and later code changes may unknowingly conflict with these dynamic modifications. This creates hidden dependencies where simply renaming a variable or reorganizing functions can silently break important logic. Because of these dangers, direct manipulation of namespaces should be reserved for tightly controlled uses, such as in frameworks or debugging tools, and must be clearly documented. Python code. Risks of modifying namespaces. This lesson shows how changing global variables can lead to confusing and fragile behavior in a program. It contrasts a safe approach, where globals are assigned in a straightforward and predictable way, with a risky approach that alters them dynamically through the globals dictionary. By comparing these two patterns, you can see why directly mutating global state at runtime makes code harder to understand, debug, and maintain, and why the simpler global assignment style is safer and more reliable. We define a constant conversion rate from miles per hour to meters per second with the value 0.44704. This constant is placed at the module level, so any part of the code that needs to convert speeds can use it. Keeping this value in one clearly defined, unchanging location makes the conversion transparent and helps prevent accidental changes or calculation errors throughout the program. A string variable is defined with the value mph to mps, and this string is used as the name of a global variable that will be added to the global namespace later in the program. By storing the name as a string, the code can change the global environment while it is running. This kind of dynamic modification can be powerful, but also introduces potential risks if it is not handled carefully. The safe speed conversion function takes a speed in miles per hour and converts it to meters per second. It does this by multiplying the input speed by a constant conversion factor that is defined once at the module level. Using this fixed constant keeps the calculation clear, stable, and easy to maintain. The function then returns the converted speed as a reliable and predictable result. The risky inject rate function takes a new rate value and, using the global namespace, assigns it to a global variable whose name is stored elsewhere. This means it can dynamically create or overwrite a global variable at runtime. After doing this, it prints a message saying which global name was updated and what the new rate is. Because it silently changes global state, this technique can cause unpredictable behavior in other parts of the program that rely on that global variable. The risky speed conversion function takes a speed in miles per hour and converts it to meters per second by multiplying it with a rate taken from the global state. Instead of using a fixed, clearly defined value, it looks up the rate using a name stored in another variable. This creates a hidden and fragile dependency because the global rate can be changed unexpectedly somewhere else in the program. As a result, the function's behavior can become unpredictable, even though it simply returns the converted speed in meters per second. This line outputs a message to the console to state that the safe conversion rate from miles per hour to meters per second is being used. It reports the specific value of this conversion rate, which was defined earlier as a constant in the code. By printing this information, the program makes the conversion factor used in the safe speed calculation clear and transparent to anyone reading the output. We use a safe speed conversion function with an input of 60 miles per hour, which relies on a predefined constant to convert this value into meters per second. The function applies this constant to perform the calculation and then prints the converted speed. This demonstrates how using a stable, clearly defined global constant provides a reliable and consistent way to handle unit conversions in a program. The risky inject rate function is called with the value 0.4 and then changes the global namespace by creating or updating a global variable named mph to MPS with that value. Because it alters global state dynamically, this can easily cause unintended problems, especially if the value is wrong or comes from untrusted sources, such as user input or configuration files. After making the change, the function prints a message saying that the global name has been injected with the new value, emphasizing how potentially dangerous this kind of dynamic modification can be. We now print the result of converting 60 miles per hour using a risky speed conversion function that depends on a global variable. This variable was injected earlier and can be changed at any time. Because the function always uses the current value of this shared variable, any unexpected change can produce an incorrect conversion. This example shows how fragile and unreliable code becomes when it depends on mutable global state. This line checks whether the global namespace already contains a specific name, using a membership test on the global's dictionary. Doing this confirms if the risky function has successfully added that name to the global scope. The outcome of the check is then printed, giving immediate feedback about the current state of the global namespace. This line of code prints the current value of a global variable called MPH to MPS by looking it up in the global namespace. It uses a function that returns all global variables as a dictionary, and then retrieves the value stored under that name, which was added earlier in a dynamic way. This shows that the global namespace can be changed at runtime and then queried, and it highlights that such dynamic modifications can be risky. This script compares a safe and a risky way to handle a conversion from miles per hour to meters per second. The safe approach uses a clearly defined constant, making the calculation predictable and reliable. The risky approach instead injects a new global variable dynamically, which can overwrite the expected conversion rate, especially if it comes from user input or configuration. When the conversion function relies on this injected value, it may produce incorrect results. The script shows this by printing the correct result first, then demonstrating how the risky method changes the outcome and leaves the unexpected variable in the global namespace, highlighting the danger of such side effects in larger programs. Safe dynamic imports. Core import mechanics. To understand safe dynamic imports in Python, it helps to know how Python loads modules in general. Python keeps a registry of modules that are already loaded and a search path for finding new ones. When you import a module, Python first checks the registry and reuses it if it is already loaded. Otherwise, it searches for the module, compiles it to bytecode if needed, runs its top-level code, and then adds it to the registry. This same process happens for both static and dynamic imports. So, importing a module always means executing its code, not just looking it up. In Python, you can import modules dynamically at runtime by calling a special function with the module name as a string. This function uses the same system as regular imports, but it checks whether the module is already loaded and either returns it or loads it as needed. The result is a live module object whose attributes and methods you can use like any other object. This approach is useful in situations such as web servers, where you may want to load plugins only when they are needed to save memory and reduce startup time. When you import a module, all of its top-level code runs, which can trigger actions like opening files or starting network connections. With dynamic imports, where the module name is chosen at runtime and may depend on user input, this can blur the line between simple configuration and actual execution. Python also caches imported modules, so later imports reuse the same module object, including any changes to its internal state. This behavior improves efficiency, but means dynamic imports can create lasting side effects on global state, so they must be designed and managed carefully. Python code, core import mechanics. This section explains how Python's import system works by using repeated imports and accessing module attributes. It shows that when a module is imported, Python stores it in a registry called sys.modules. Because of this caching, the top-level code in a module runs only the first time it is imported, and later imports reuse the already loaded module without executing that top-level code again. We begin by importing the import library, which lets us load modules dynamically when their names are only known at runtime. We also import the system library, which provides access to system-level information and tools. In this case, the system library is used to access the registry of loaded modules so we can check which modules have already been imported. This code checks whether the math module is already loaded by looking it up in Python's internal registry of modules. If math is not found there, it is then imported using the importlib library, which loads it into the registry. This behavior shows that Python caches imported modules so their top-level code runs only once, even if you import the same module multiple times. After the math module is first imported, the code checks the system's module registry to confirm that this module is now loaded and stored in memory. It then obtains the unique identifier of the math module object. Seeing the same identifier on later imports shows that Python reuses the same module instance rather than loading it again. This confirms that repeated imports are efficient because the module is cached. We use the import module function from the import library to import the math module again, but Python does not actually reload it. Instead, it looks in its internal cache of loaded modules and returns the existing math module object. When we print the unique identifier of this second import, it matches the identifier from the first import. This confirms that Python reuses the same module object in memory, rather than creating a new one each time it is imported. This line checks whether the two variables that hold the imported math module actually refer to the same object in memory. By using the identity comparison, it shows that Python reuses the same module object when a module is imported more than once. This happens because Python caches imported modules. As a result, importing a module multiple times does not reload it, but instead retrieves the existing version from the cache, which improves efficiency. This script explains how Python handles imports by showing that modules are cached after the first use. It starts by checking that the math module is not yet in the system's registry, then imports it and confirms it is now registered. When the math module is imported again, the script shows that Python reuses the same module object by comparing their identities. This behavior means Python only runs a module's top-level code once, and later imports simply retrieve the already loaded module from the cache, which improves efficiency. String-based imports. Dynamic imports allow a program to load modules at runtime using names provided as strings, which can come from sources like configuration files or user input. This makes it possible to build flexible systems, such as plugin architectures, where new features are added simply by listing module names. However, this flexibility adds complexity and risk because the program must manage these imports while running and verify that the loaded modules follow the expected interfaces, unlike static imports that are fixed in the code. Imagine a data processing framework for university research teams, where each team provides its own analysis module, and all modules are listed in a central configuration file. When the framework starts, it reads this file and dynamically imports each module by name, expecting certain functions or classes for tasks like validation and analysis. This lets the framework work with many different modules without knowing their names ahead of time, which makes it very flexible. However, if a module name is wrong or a module does not provide the expected features, the problem only appears at import time, showing the risks of relying on string-based imports. When you use a module name given as a string for dynamic imports, you are effectively allowing that string to trigger code execution, so it must be handled very carefully. Never import a module directly from an arbitrary or untrusted string. Instead, restrict imports to a whitelist of approved module names or map user-facing names to vetted modules. After importing, immediately check that the module has the expected interface, such as required attributes or behaviors. In critical systems like financial or medical software, these safeguards are essential to avoid misconfigurations and reduce security risks. Python code, string-based imports. This material explains how to use dynamic, string-based imports with simple tool modules while keeping the process safe. It shows how to map user choices to internal module names in a controlled way, rather than importing whatever the user types. It also emphasizes checking that any imported module actually provides the expected functions or attributes before using them. Together, these steps help ensure that dynamic imports remain predictable and secure. We begin by importing the types module, which lets us create new module objects dynamically. We also import the ImportLib module, which allows us to load other modules using their names as strings. Together, these imports provide the basic tools the script needs for dynamic module creation and programmatic importing later on. We create a fake module to act as a length conversion tool using a feature that lets us define modules dynamically. This module is given the name LengthToolsModule. We then add an attribute called toolName and set it to lengthConversionTool to describe what it is. Next, we add a describe attribute implemented as a small function that returns a short explanation saying the tool safely converts inches to feet. Altogether, this lets us simulate a custom module with specific descriptive behavior for demonstration purposes. We create a new module object to act as a temperature conversion tool, giving it the name TempToolsModule. We then add an attribute called toolName and set it to temperature conversion tool so its purpose is clear. Next, we define another attribute named describe as a small function that returns the phrase converts Fahrenheit to Celsius. Together, these attributes label the module and briefly explain that its role is to convert temperatures from Fahrenheit to Celsius. We first import the system module so we can interact with the Python runtime. Then we insert our fake length conversion module into the system's module registry using its name, which effectively registers it for dynamic importing. We repeat this for the temperature conversion module, so both modules can be accessed by their names. This setup is essential because it lets us safely map user choices to these internal module names and load the correct module at runtime based on user input. We use a dictionary called the Safe Tool Map to connect user-friendly tool names to their internal module names. This lets the system take a tool name chosen by the user and reliably match it to the correct module behind the scenes. By relying on this controlled mapping instead of raw user input, we avoid unsafe or incorrect module imports. As a result, the system becomes more secure and more dependable. In this example, we simulate a user making a choice, such as one read from a configuration file or entered directly by the user. The choice is stored as a text value, in this case, the word length. We then display this choice to confirm what the user requested. This confirmation step is important for debugging and for making sure the correct tool is selected based on the user's input. We first use a predefined safe mapping to translate the user's friendly tool name into the actual internal module name. This mapping only allows known, trusted names, so the user's choice is treated as a key, and any arbitrary or unsafe input is rejected. By doing this, we ensure that only valid and secure module names are used, which helps prevent security issues. After resolving the module name, we print it to confirm that the correct module has been selected based on the user's choice. We use dynamic importing to load a module whose name is stored as a text value, relying on the import function from the importlib module to load it at runtime. After the module is imported, we access its tool name attribute and print it. Seeing the expected tool name confirms that the module was successfully loaded and that it provides the attribute we need, which helps verify that the module behaves as intended. The code first checks whether the imported module has a describe feature to confirm it supports the expected functionality before using it. If this feature is present, it calls it to print a user-friendly description of what the tool does. If the feature is missing, it instead prints a message explaining that the chosen module does not provide the required describe capability. This simple check helps avoid runtime errors by ensuring the module matches the expected interface before the program continues. This script shows how to use dynamic imports based on string module names in a safe way. It creates two mock tools, one for length conversion and one for temperature conversion, each with a descriptive attribute, and registers them in the system's module dictionary. A secure mapping connects simple user choices, such as length, to the correct internal module names. When the user selects length, the script looks up the corresponding module name, imports that module dynamically, checks that it has the expected describe attribute, and then reads out the tool's description. This design allows flexible, user-driven module loading while keeping control over which modules can be imported. Safer dynamic imports. When using dynamic imports, treat every imported module as untrusted, even if it is part of your own project. The import mechanism is powerful but risky. especially when user input influences what gets imported, because it can load the wrong module or even malicious code. To reduce this risk, centralize all dynamic imports in a single, carefully reviewed component. In that component, enforce strict rules, such as only allowing imports from a predefined list of modules or from a specific package namespace, so you tightly control what is allowed to be loaded. When using dynamic imports, never rely directly on raw user input, because it should be treated as untrusted. Instead, validate the input or convert it into safe, predefined values. In a plugin system, for example, let users choose from an approved list of module names that you map to internal identifiers you control. This approach prevents users from importing unintended modules and keeps you in control of what can be loaded, improving both security and reliability. When using dynamic imports, you should always plan for failures and handle them safely. Imports can fail because modules are missing or versions do not match, so your code should catch these errors, log what happened, and fall back to safe defaults instead of crashing. For example, if a web app cannot load a specific tax module, it should automatically switch to a generic one and record the problem for later review. This approach keeps your system flexible while still maintaining reliability and security, making dynamic imports a controlled and safe part of your design. Python code, safer dynamic imports. This lesson focuses on using a simple plugin registry to make dynamic imports safer. Instead of importing any module name provided by a user, you keep a controlled list of allowed plugins and only load modules that appear in this registry. This approach prevents arbitrary or malicious imports while still allowing flexible, pluggable behavior. You also learn to handle missing plugins gracefully, for example, by reporting the problem or falling back to a default, so the program continues running instead of crashing. The code first imports the import lib module so it can load other modules dynamically while the program is running. For example, based on user input or changing conditions. It also imports the module type class from the types module. This class is used in type hints to indicate that a variable should hold a module, which makes the code clearer and helps with error checking. We define a plugin registry as a dictionary that maps user-friendly names to internal module names. For instance, a label like sales tax might be mapped to a math module, and shipping cost might be mapped to a statistics module, even if these are just stand-ins for the real logic. By using this registry, we control exactly which modules can be imported in response to user input. This ensures that only safe, predefined modules are loaded dynamically, rather than allowing arbitrary imports. In this example, we simulate a user choosing a plugin by a friendly name, such as sales tax, to show how that choice can be safely mapped to an internal module name. The user selection could instead be shipping cost or an unknown option to test different behaviors. The main goal is to demonstrate a safe way to translate user input into internal module references without directly importing modules based on whatever the user types. This helps prevent unsafe or unintended imports while still allowing flexible user choices. We first use the plugin registry to translate the user's friendly plugin name into the actual internal module name. The registry acts as a controlled map from allowed user choices to real modules in the program. By using the user selection only as a key in this registry, we ensure that only predefined trusted modules can be imported. This prevents users from triggering arbitrary or malicious imports outside the approved set. The program first checks whether the internal plugin name exists in the registry. If it is missing, it reports that an unknown plugin was requested and sets the plugin module to a safe default of none. If the name is found, it tries to load the plugin dynamically using the import library. When this import succeeds, it confirms that the module was loaded safely. If an import error occurs, it reports the failure and again sets the plugin module to none, so the program can continue with a fallback instead of crashing. If the plugin module loads successfully, we use it to perform a simple tax calculation. We take a purchase amount of $100, apply a tax rate of 7%, and compute the resulting tax by multiplying the amount by the rate. We then output the tax value in dollars. If the plugin module is not loaded, we instead report that fallback behavior is used and no plugin-based calculations are performed. This script shows a safer way to use dynamic imports by relying on a plugin registry. It keeps a mapping from user-friendly names to approved internal modules, so only predefined plugins can be loaded. When the program runs, it checks the user's choice against this registry and, if valid, imports the module and uses it to calculate a sample sales tax. If the module is missing or the choice is not recognized, the script falls back to a safe default and skips the calculation. This design prevents arbitrary imports and handles missing plugins without crashing the program. In this lecture, you learned to use Open with context managers to read from and write to files safely, specifying modes and encodings. Inspect and, when necessary, modify global and local namespaces using globals and locals in controlled scenarios. And use import symbol for dynamic imports while understanding its risks and preferring higher-level alternatives when possible. In the next module, Module 10, we will go over Advanced and MISC. Thank you for your attention. See you all in the next lecture.